Good morning, everybody in Thailand. Good evening from the USA. I hope everybody is doing well and keeping safe. And welcome back to everybody who joined us 2 weeks ago for the Condensable PM webinar. As Sam mentioned, today we're going to talk about basically the flow measurement per the US EPA and the 3 different methods that are outlined by the US EPA for measuring flow, how each of those methods use what equipment, and finally we'll discuss why there are differences in these methods and what they try to achieve. So let's start off with looking at, blow this up. So for everybody who is an experienced stack tester or have at least done some kind of stack testing per US EPA Method 5, you will know that by achieving Method 5, you need to perform methods 1, 2, 3, and 4 before you go ahead with your method 5 PM sampling. And it's those methods that gather site-specific information to help you with your isokinetic calculations. So therefore, I would say that almost everybody here would be familiar with the basic method 2 as per the isokinetic standards that you're probably already performing. And method 2 per the EPA states that it is the determination of stack gas velocity and volumetric flow rate. And again, as you know, you perform this method 2 to use some of this information for the determination of your nozzle size, for the determination of your K factor, and other parameters within your isokinetic sampling. So method 2 is applicable for measurements of the average velocity of a gas stream with a pitot, and most people as well would probably be familiar with the S-type pitot, the one you can see here in the picture right beside the nozzle. There, your S-type pitot will have your impact pressure on the bottom side facing into your flow, and you will have your negative pressure on the top side. And I'm sure everybody is familiar with this piece of equipment. So the average gas velocity as a stack is, as we know, determined from the gas density and from measurement of the average velocity with an S-type pitot tube. And as you know, we take multiple measurements of that flow rate across the stack because we know that the stack is typically not uniform in its flow rate. And that's how we determine our average flow rate for our traditional isokinetic sampling. And then as you know, the volumetric flow rates are adjusted mathematically for temperature, pressure, gas molecular weight, things like variables that can be standardized to then allow us to compare stacks of different temperatures or pressure against each other against a standardized volume that we've determined from our flow rate. However, method 2 does have its limitations to accuracy. It does provide us enough information when we're performing something like a method 5 test, but there are situations, which I'll talk about a little bit later in our presentation today, that requires more accurate measurement of flow. So let's take a quick look at what we typically talk about in terms of flow characteristics inside a stack. So laminar flow in a stack is where method 2 would be appropriate and yields accurate results when the flow is flowing directly up from all points across the stack, regardless of where you take your measurement. The gas is flowing directly up, parallel, side by side to the walls of the stack, and therefore the S-type pitot, once placed into that flow, is in direct alignment with the flow of the stack. The bottom of the S-type pitot, the impact point, is hitting directly into the flow. And in these situations, we can get a very, very accurate or fairly accurate flow measurement using an S-type pitot. Those of you who have been in the industry a while and been at several sites, you'll know purely by performing some of your isokinetic sampling that you very rarely get exact laminar flow in a stack. A lot of times it is what we would consider non-laminar flow. And if we were to measure via method 2, a traditional method 2, as written by the EPA, using an S-type pitot, the probability is that the method 2 using an S-type pitot will yield us artificially high results with a non-laminar flow. And as you can see, the non-laminar flow is anything that is not coming straight up. So it may be going back and forth, zigzagging across the stack, or it could be cyclonic flow, which is going around and around the stack as it goes up to the top. So knowing this situation, how can we adapt to the unique stack parameters and get an accurate flow measurement for whatever purposes that we're doing? And the EPA gives us two methods to allow us to achieve this. The first would be method 2G, where you can see is the determination of stack gas velocity and volumetric flow rate with a two-dimensional probe or pitot. And then method 2F, which is the same determination of stack gas velocity and volumetric flow rate, but it's using a three-dimensional pitot in this situation. So let's take a look first at method 2G using our 2D probe. So when we talk about method 2G, we're using a two-dimensional probe, and what it does is it can help us measure in what we say in English is a yaw angle flow. And I found this diagram here to try and help explain what yaw angle is as compared to laminar flow. So for example, as you can see there in the little diagram on the left, we have a paper airplane. And on the y-axis going straight up in green is what we would consider our laminar flow. It's flowing directly up the stack in a straight line. Now, what we can do, as you can see, if that paper airplane or the probe in our situation is sitting directly into the stack, our yaw angle would be if we move the probe from left to right, but keeping it in the straight line as we did when we put the probe into the stack. So what a two-dimensional probe will do is it will help us determine any yaw angle flow coming up the stack. Okay, it will actually help us measure two different points simultaneously. It will help us measure our direct impact point as well as our yaw angle there. And how do we do this? Here's another quick diagram for you. So you can see here in our image the end view of the probe, where the probe is pointed directly into the stack there in the middle, and the flow is coming up that stack. Our yaw angle will be negative to the left if the flow is left, or positive yaw angle to the right. So I hope that kind of helps explain what would be considered a yaw angle for this method 2D probe. And here is a image of the 2D probe. Now, as you can see here in the middle, we have our basic impact, positive impact point here. And you can see on either side of the probe here at very specific angles as determined by the EPA, we have our yaw angle pitot inlets to help us measure any yaw angle, or what would be probably most likely cyclonic flow coming from right to left or left to right inside of the stack. So this is an image of the pitot head. Now, I want to make it clear that the EPA does not allow the use of 2D or 3D probe heads in conjunction with, or to be used with, a isokinetic nozzle when you're doing isokinetic sampling. If you do have such turbulent flow and you want a more accurate flow rate, you would perform your method 2G or 2F using this equipment in your setup process. So you would do your method 1, then you would do either a method 2G or 2F, method 3, 4, then during your method 5 sampling, you would continue to use your S-type pitot for your delta H, delta P adjustment. But what the method 2G would give you would be a more accurate flow determination when you make your calculations for your mass flow rate, how much emissions is actually coming out of the stack. So it can get a little bit complex, but I just wanted to point that out, that this is a standalone method and it would not be used during a method 5 or a method 29 for metals or any other isokinetic method. So we also talked about method 2F, and 2F is what is considered using a 3-dimensional probe or pitot. And what it would do is method 2F will measure both the yaw angle that we discussed in the last slide, and it will also measure the pitch angle. So if you can imagine, we looked at this image here on the right. We had our y-axis as our laminar flow. We have our yaw, which is side to side, left to right. Now, at the same time, if we needed to, we can also measure our pitch, which is up and down measurement in reference to a straight probe. We can either measure up or down. And that's up and down from the neutral or flat angle of a probe being entered into the stack. And in this situation, you can see here, if this was our probe here, you can see that our y-axis and our x-axis would be the top and bottom. Disregard the flow here. I'm trying to show you that you could measure flow coming in at this angle or down at this angle inside of a stack, and that would be our pitch angle. So again, we would be measuring 3 dimensions. We would be measuring our laminar direct flow. We would be measuring our yaw angle, and we would also be measuring our pitch angle. Oh. And this here is an example of what would be the modification on a 3D probe. It looks very, very similar to our 2D with our direct impact here and our yaw angle measurement here. Now you can see, and it's a little hard to see here, but you can see right here in the sides would be our pitch angle inlets. And there's actually one here on the other side as well that you can't see in this picture. But now you're measuring 5 points simultaneously for this particular method. So now you're taking quite a bit of flow information and determining, or almost, for a lack of a better term, creating a model of which way the gas is flowing inside a stack so we can get an accurate reading of the total mass of volume flowing through that stack. So most of you may be thinking now, we've gone from a 2-position or 2-measurement S-type pitot, measuring 2 points, to 3 points or 5 points. How do we go about measuring all of that information? So we have 2 options that would be available in this typical situation. It would be our manual XC3D55 system. And as you can see here, we would have at the front of our probe our 2-dimensional or 3-dimensional pitot. We would have here what is considered our probe extension. So we can make this longer and shorter as we go across and back and forth across the stack, hitting our traverse points and measuring each point that we need to measure, just like we do in a regular method 1 determination of our sample points for our isokinetic sampling. We do the exact same here for our method 2F or 2G sampling, when we determine exactly where we're going to be sampling inside the stack. And then what this system will also do, it will allow us to measure the 3 or the 5 lines or 5 impact points simultaneously for us to determine our yaw or our yaw and pitch angle. Okay. So you can see here on the manual console, we have our red line displays for our pressures on each of those individual impact points on the probe. We have an inlet for our temperature as determined by our regular method 2. We also need to measure our temperature for our calculations, our flow calculations, and our magna helix here, also measuring our impact pressure for our sampling. So this would be considered a manual system to perform method 2F or 2G. You would have to do and perform all of the calculations manually and have an understanding of those, and record all the information manually when you are performing this testing. What is helpful here is, as you can see inside, there's a box here attached to the back side of this probe. This box actually has an inclinometer in it. So as we rotate the probe to what's called a null position, where if we have flow, and I'll just stop presenting for a minute. So if this is our stack, we enter our stack and our flow is coming down to the side. What we're going to do is we're actually going to tilt and turn the probe into the flow until we get basically what would be considered a 0 reading on that plane. So now we know that that particular flow element is coming at the probe at 15 degrees or 20 degrees or 90 degrees, I guess would be very extreme, but possible. And we need to know that angle in part of our calculations to help determine our flow rate. So that inclinometer will make that measurement there for us. Now, I also want to share that we do have our AccuFlow system, which is our completely automated system here, kind of like our XC5000 console for isokinetic sampling. And what this console will do is it's connected via a laptop and software connected to our AccuFlow box. And what this box will do is it will help us again record our null angle and our yaw angle, pitch angle if we need it. And it will also has digital pressure sensors in here rather than our magnehelic for recording all of the pressure data coming from the 3 or the 5-hole pitot that we have attached for this method. What you can see here is an example of a single setup, and I think I may have left it out of my presentation, but let me jump over here real quick and show everybody while I have you. The AccuFlow can actually be set up with multiple, just thinking about it. You go to my systems here. We can actually, you can see here on this image, we can actually configure and set the AccuFlow system up to simultaneously read 1, 2, 3, or even 4 probes at the same time. So instead of having to traverse maybe all 12 or 16 points across the stack with one single probe, if you wanted, we could actually have 4 different probes attached to one single laptop and sample 4 points simultaneously, and then move all of those traverse all of those pitots outwards in the stack at the same time, and record the next points and the next points and the next points. Depending on the accuracy that you need and what's determined by local regulations, these particular systems could save hours and hours of sampling time doing 4 pitots at the same time rather than doing 1 and traversing all the way around the stack. And this is something that has been useful here in the US for determining accurate flow rates for things like Performance Specifications 11, which is online PM SEMS equipment, or other SEMS type equipment that is going to be permanently installed. Maybe a flow SEMS needs to be calibrated in a stack when it's first installed. That will allow us to get very accurate measurement to be able to create a very, very good calibration for a device like that. So just a little bit of side information for everybody. We talk about accuracy and why these measurements are so important. And the National Institute of Standards here in the United States, as well as KTL, which is the local Korean government body down in Korea, equivalent to NEEDISS here in the United States, over the last several years have been collaborating in flow studies trying to determine the actual accuracy of different pitot designs. And to give everybody an example of some of the early data that's being released from this study is a standard pitot, so just our L-type pitot, standard type pitot is what it's called, has an accuracy of plus or minus about 20%, okay? When we look at an S-type pitot that everybody probably here is very familiar with using for their isokinetic sampling, we bring our accuracy down to about a plus or minus 10% range, depending on the construction of the pitot and other small variables, but it's about a 10% plus or minus 10% accuracy in the reading of that S-type pitot. Now, when we get to a 2D pitot, current data seems to show that we're getting down to close to the plus or minus 1% accuracy range of measuring flow. And 3D pitots are showing that they are even accurate again, somewhere around the plus or minus 1% accuracy when measuring flow. And this has been quite an interesting research project. And there's a lot of discussions at the EPA about the possibility of changing or upgrading some methods in the future, replacing the requirements or the standard requirement for an S-type pitot and increasing the accuracy of flow measurement by trying to encourage other technologies like the 2D and 3D. So why is accuracy so important? Why now are people looking at this when S-type pitots have been used basically since the 1970s when isokinetic sampling was first developed by the EPA? And there's been several changes really in the way that either regulatory agencies or government or private industry is using the data, flow data. And one of those examples is a cap and trade initiatives that are coming to many countries now around the world, where there's companies are paying a certain designated amount, say per ton of a certain emission that's put into the atmosphere. And they also have the right to trade that some of their emission limit to another customer, basically sell that to them and allow them to emit more emissions on the basis that they are going to pay a higher rate for that particular higher emission. Now, obviously, when you're talking millions and millions of US dollars for a particular emission, ton emission limit over a year span, you want the most accurate data as possible. Plus or minus 10% is most likely not acceptable because that could end up being 10 million, 20 million extra dollars for private industry, or vice versa. If it's undercalculated, 10 or 20 million dollars less revenue for government if they are charging private industry for these emission rates. So flow accuracy has become very, very important for a lot of industries from a financial perspective. Another reason is emission limit accuracy. If you have a facility that has what we call here in the United States a Title V permit, and within that operating permit states exactly how much of a particular emission you can release into the atmosphere every year, you want that measurement to be as accurate as possible because there are substantially large fines for exceeding your Title V emission limits as specified in your operating permit. And then finally, as everybody's seen, in situ SEMS, whether it be NOx or SOx or mercury or even flow SEMS themselves, are becoming more and more common in facilities. And to assist in determining an accurate mass emission rate, an accurate flow rate must be determined to help the accuracy of that SEMS unit. Just like a mercury SEMS is typically calibrated, or in the US we say rated, relative accuracy test audit against the reference method, which is, in our case, the sorbent trap method, method 30B. You would take your 30B test and measure it against your mercury SEMS to calibrate its calculations. The same, we want to do that for our flow SEMS and the flow data that's being transferred into any SEMS system on a facility. So we want to audit that flow SEMS using the most accurate primary standard that we have, which would be a method 2F or a 2G sampling. So I kept it kind of light today. I didn't want to go into too much big detail for calculations. Today's mission here was to give everybody an overview of what these methods are and the types of equipment, very, very unique equipment that is used for these particular method 2F and 2G measurements. It might be the first time a lot of people are seeing this, but we wanted to make you aware that this equipment is available. And if you have customers questioning accuracies or flow, wanting better flow data because they realize the financial implications of what they may be paying for their emissions, that this technology is available. It is approved by the US EPA, and it's used very, very widely, and it's continuing to grow in the market as a request from customers all around the world, to be honest with you. So at that point, I might quickly pause to see if anyone has any questions. Sam, did you receive any written questions? Anything?
Does anyone have any questions? มีใครจะถามคำถามอะไรไหมครับเป็นภาษาไทยก็ได้ค่ะจะลองแปลให้นะคะหรือว่าถ้าไม่ถนัดพูดก็สามารถพิมพ์ได้ค่ะก็คือจดสามารถกดที่ตัว conversation นะคะด้านบนน่าจะด้านบนของทุกท่านนะคะ Okay, I have one more question about the consoles of the standalone of the two type. One of them is like a manually with the XC
3D 55. Yep.
And with something like a acute flow. What is the main point difference between of this?
So let me just jump back to my slide here and show real quick. So the main difference between these two would be to say that the 3D 55 system here, as you can see, would be considered a manual system. The the little console box there, which is quite small. It's about the size of a very small laptop, is making a manual reading of the pressures coming from the pitot, but none of that information is recorded or calculated inside of that console. It's just displayed as a value, and you would have to manually record all of that information when you're sampling. Now, the AccuFlow is designed against the methods themselves. So inside the software based in the laptop, you would select either method 2, 2F, or 2G, and the console itself will actually do the method calculations for you. It will record all of the data coming from the pitot, and it will give you a report in an Excel spreadsheet that you can then use for future calculations, whether it be for SEMS calibration or for determining mass flow rates or whatever you want to use that information for. But it's basically an automated version of the manual console. Okay.
Okay.
Yep.
Yeah.
So I hope that helps there.
So that's mean with the XC3TD55 with the manual console, we must know the angle between the measuring when we measuring the different of the degree of the angle, right?
Correct. So typically what you would do is you would have a manual inclinometer on the back of the probe, like a device that shows you the angle, and the operator of the probe would turn the probe until on the console here you can read. Let me show you right here. Let me just bring it up one more time. Basically, you can use the measurement in the magna here, like this dial right here. You can use that to angle the probe to basically what is considered null or zero in English, directly into the flow. And then you would take a manual reading of that angle based on a manual, and I'll show you like a manual one here, inclinometer. I'm just trying to remember where on our website that is. Let me just look real quick at one thing. Trying to remember where that is in our book. It's in here. So you would use a device like this. Can you guys see my screen? I'm not sure if you can. Let me bring that up here. So right here is an example of a manual incline manometer, like this one here. And this would, as you rotate the probe, you can take an angle reading manually. Whereas the AccuFlow will actually display that value, that angle on the screen automatically, included in that little kind of sensor box that hangs off the back of that probe.
Okay, thank you. We got the one question from Mr. Craig. Which stack type would be used for this probe, and could it be used with the original console, or should buy the new one for this? And he asked about the price.
Okay, I'll let you figure the price out down there. Yeah, but so you would do this sampling at the same location that you would do your method 5 isokinetic sampling. So I have here hidden in my slides, but I can open this for you. I actually had it hidden here. Let me unhide this slide and then show it to you. So you would do what you would typically do in your method 1. If you don't know the measuring level that you would typically do for your method 5 sampling, you can determine that by US.EPA Method 1 sighting criteria, whereas it states you need to have 8 diameters of the stack upstream, going up, and 2 diameters of the stack coming down at least from your exit. So let's use an easy round number. The number, say it's a 1 meter stack. You need to be 8 meters past the last disturbance, and a disturbance would be a bend in the tubing of the stack, maybe a fan or something located inside of the stack that could create turbulence for you in that air. And then you need to be at least 2 meters down from the exit into the ambient air. So for method 2F and 2G, you would use this same method 1 calculations to determine the best place to sample, as you would for a method 5. Now, keep in mind that oftentimes facilities and customers are requesting more accurate flow measurements in locations that are not exactly will meet method 1. They may have very unique situations with their stack, and they do want to measure in locations where there is quite a lot of turbulence. Maybe you are measuring down here at the bend or something that is creating them problems, and they want to know what is happening with that flow. You technically not meeting the method. However, in that situation, you are performing more of a research test rather than a test that you're going to be used for reporting values to the government. So in that situation, the equipment will work just fine. Just keep in mind you're taking a change to the method in terms of the location. In terms of the measuring console, unfortunately, yes, it's not possible to use your regular isokinetic console because it only has 2 pressure lines coming in for your S-type pitot. And at minimum for our 2G, we need a 3rd pressure line, and for our 2F, we need 5 in total. So unless you want to theoretically sit 2 isokinetic consoles or 3 isokinetic consoles side by side, it's really not possible to do. So you would need a new device to be able to perform these methods accurately.
Okay. I need to clear about his question with the stack type. That means whatever type you need to more accuracy and some limit of the stack, right?
Mm-hmm. So you could typically tell if you're an experienced stack tester and you go to a location, you can typically tell if you have yaw, pitch, cyclonic flow, anything like that in a stack. One good giveaway is a lot of vibration on the stack. The stack is moving and moving constantly because the air is bouncing back and forth like this. Another good way to determine if you have cyclonic flow or bouncing flow is if you've sampled this location before and you are sampling points 1, 2, and 3 across the stack, and you move your Method 5 Pro to location number 4, and all of a sudden your delta P reading goes really high or really low compared to what the delta P was on the other side of the stack. It means you have gas not moving uniformly. It's either low on this side or high over here, or high and low, depending on which way your delta P reading moves when you move your pitot. So even though your S-type pitot can give you a measurement average accurate enough for your isokinetic sampling, if you're really determining an exact flow rate of the stack, let's say how many tons of SO2 is being emitted over an entire year, then your S-type pitot average is not going to be quite as accurate as a 2F or 2G measurement that will be much more precise and probably allow the customer to pay less in emission fines or whatever it may be, or help them determine maybe if a new piece of mitigation equipment, a new bag house, or a new ESP or something that they've added to reduce the emissions, if it's really helping or not.
Okay. So my last question is about the flow measuring in the process. Some customer require for the process flow monitoring in the like a vertical duct or some kind of the before the back filter or after the filter. Sometimes the pressure is very high. What about the limit of the pressure for this kind of the transducer?
So there's no real pressure limits per se in terms of the measuring. Obviously, you could have positive or negative pressure, which shouldn't really affect the sampling too much, because we're using the natural flow of the gas to read the pressure. It can be a challenge sometimes isokinetic sampling with negative pressure. You need the vacuum to pull very hard against the gas that's being sucked into the stack. That could be very, very difficult. But in terms of pressures for this particular measurement, it's really not a big problem. At the same time, measuring vertical versus horizontal, or round versus square or rectangular duct is also okay. All of these parameters can be taken into account with your Method 1 determination, and all of those can meet the method no problem at all. So the biggest challenge, I think, in those situations will be, do you have enough distance between each of those turbulences to measure? Most cases, no. But when you're measuring close to those particular pieces of equipment, the reason you're measuring is you want to know what the gas is doing. Is it moving this way? Is it moving back and forth? Which way is it moving? So again, you're really performing a research study rather than performing a compliance measurement to report to the government. You're really only using that information to give it to the customer so they can make maybe better decisions about design or adding equipment or things like that. So that would be perfectly fine in those situations.
Okay. So just as one more question. Sure. we got the question from Mr. Curtis. Yeah.
Click on, oh, where'd it go? Last question for me today. Found the flow not stacked to the wall. Should we need to move the probe debris, which is not normal? So I think the best way to answer this is if you know that the flow is on an angle, so if we think of this as normal, okay, and we think of this as what we discover in the stack, then theoretically, yes, if we were to do if we figure this out and we figure out we want to do a method 5, our method 5 should be done on the angle like this. So the probe, the nozzle won't be in the stack directly like this. It may be turned like this. And we're actually going to be measuring the flow coming directly into our probe. That would be the best option, like this. Now keep in mind, as we move, we might need to slightly move our probe angle, or maybe on the other side it's coming back at us as it comes around. It's coming back at the probe this way, so we need to move our probe on that angle. But yes, you would typically angle your method 5 probe accordingly. And this is a great way to discover that.
Okay, and
I hope that answers that question.
And as you mentioned about the different type of method, okay, after different type of the pivot, like a pivot type L, S, and between the 2D probe. So what have you tried to compare with the average pivot? The average pivot is the like the market pivot for the same, for the full SEM. As you know, we are the distributor for SEM as well.
Right. Absolutely.
And I install to the customer side with the average pivot. It means the pivot have a one tube insert to the stack, and they have a point.
It has multiple holes. Yes. Honestly, Sam, I do not know the accuracy of that, but from my understanding, that is a very, very accurate measurement.
Yes.
For total laminar flow, okay? Because you're measuring every point simultaneously. So it might be high here, low here, but you're getting a real-time average. Yeah. What I don't know is how accurate they are for pitch or yaw measurement. Because my understanding is they're pointing only straight down, correct?
Yes. No,
so if you have yaw, if you have pitch, I don't know. Yeah.
Okay.
Maybe this is a new product we need to invent.
Okay. I think we have all questions for today. That's all for today. Please keep in mind, if you have any question after this, you can leave the message on the line or can reply the email. Then we will send you the certificate of this webinar as well. So thank you very much for everyone, and thank you very much, Nick. Hope to see you.
Thank you, everybody. Have a great Tuesday in Thailand.
Okay.
Thank you.
Thank you very much. Okay.
Thank you. Take care.
Okay, bye-bye.